Thank you, Eric. Thank you, Eric, for the introduction and for the possibility to participate to this workshop. So I'm going to give you an overview of most of the work we did on time splitting for incompressible fluid structure interaction. And this is a very collaborative work. So I list here the main contributors to that work. So Eric Borman, Rebecca Dorst, Jean-Frédéric Gerbeau, Céline Gramont, Johnny Goodman, Mikel Landajuela, Jimmy Muraler, and Marina Vidrasco. So a few words about the motivations of this work. So we basically are interested in the coupling of an incompressible fluid, generally viscous, with an elastic structure. And this is something that you can find in many applications, in particular in nature and in fluid flows. And this is basically our main target application. So simulation of biofluid flows, and in particular cardiac fluid structure interaction. And I very much like to say that cardiac fluid structure interaction is the typical archetypal example of fluid structure interaction, in the sense that you have in fact in this simple application all the difficulties that you may imagine in fluid structure interaction. So large displacement, contact, high pressure drops, changing topology, etc., etc. And so you really need efficient methods to simulate this kind of system. So just to start the discussion, a few words about the mathematical models that we are going to consider here, or that we want to approximate. So basically we consider two cases, one with thick wall solids and the second with shell models. So so here you see the system that we want to solve. So the structure nonlinear elastodynamics. So you have the equilibrium of momentum here. So d dot the velocity, d the displacement p, the first Euler proposed tensors, and then you have the velocity relation here, displacement velocity relation. Navier-Stokes for the fluid here in LE formulation, in the sense that we basically parameterize the do you see my pointer? Because I'm using it and I don't know if you see it.
Yes, I see it. We see it.
Okay, perfect. I'm going to minimize. Yeah, that is going to see. So you see that we parameterize, in fact, the motion of the fluid domain through a map A, which basically allows you to move the mesh in the at the discrete level. Okay, and so this is very inconvenient to discretize, in fact, the time derivative. And this is because we give us a natural sense to the discretization of the Eulerian quotient, in fact. So basically we replace the Eulerian derivative by this new term here, two terms that are compatible with the fact that you do backward difference, for instance, for the discretization of the time derivative. And then you have these two coupled systems, and you have interface conditions that are basically of three kinds. So the first one is just a geometrical compatibility condition. It basically says that, well, oh, I think this slide is fixed. I don't know why. Yeah, okay, it's the pointer. So basically says that the displacement of the fluid domain, in fact, is giving us a lifting of the motion of the interface, of the solid on the interface, okay? So X is an arbitrary lifting operator, in the sense that you only need to prescribe the motion of the fluid domain on the interface, and that inside is arbitrary, okay? And then you can compute W, which is the velocity of the fluid domain, and of course update the computational domain in the fluid through the application A, identity plus the displacement. Then you have, of course, continuity of velocity, so kinematic compunity and equilibrium of stresses across the interface. Okay, so here this G as the Jacobian of the in the fluid domain, just because we transport the fluid, we write here the stresses of the fluid on the reference configuration, and so we have these Euler terms here. F is the gradient of the application A. Okay, so this is for so U the velocity, P the pressure. Okay, so this we want to solve for D dot D, U and P. Okay. And then we can consider also the case in which if the solid is thin wall, we can consider a simplified model, for instance, shell models, where basically the equilibrium equations in the solid are written on the mid-surface, okay? And so mid-surface here means that the interface now between the fluid and the solid becomes the computational domain for the solid. And you see that we are doing here an assumption in the fact that we neglect the impact of the thickness on the coupling, because basically now the fluid is occupying that region up to the mid surface. Okay, so this we do a modeling error here, which is of order the thickness. Okay, but it's very appealing for the computational point of view. But we are making a modeling error here. Okay, so you see here an extra formulation. So basically we have the solid equilibrium now that is written on the interface on sigma on the mid surface. So epsilon is the thickness. Now we integrate the equations across the thickness, and of course appears on the inertial term. And now I written on this LD operator that can be nonlinear all the elastic operator of your shell. Okay, you see here that I only have one unknown, D, but in practice, for instance, if you consider random median shell, you only have the director Bertos of the rotations of the normal in the linear case. So you may have additional unknowns here, okay? But for simplicity, I only put the displacement. So you have the velocity relation here, and now the coupling is a little bit different in the sense that the interface condition, the equilibrium condition on the stresses is not anymore a boundary condition for the shell, it's a source term. Okay, so if you replace take here the traction, you have a boundary, a source term, and not anymore a boundary condition. Okay. Okay, so now I'm going to just make some observation on two things, on solution procedure. So what is the framework for the solution of this system, and the spatial discretization. So the first thing is that basically you have two main paradigms to solve this kind of couple problem: is monolithic and partition solution procedure. So in partition methods, these kind of things were mentioned yesterday. So you basically have two independent solvers for the fluid and the solid that can be different libraries, different approximations on each subdomain, and then you have a master code or a coupler that is basically exchanging information here, basically the primary dual variable, so velocity and stresses across the interface, and then you get the coupled solution either by splitting in time or by iteration between the two subdomains. Okay, and then you have the opposite approach is to basically build a new solver for your FSI system, and you have a big system that is solved by basically not distinguish between each subdomain. Okay, and this is monolithic approach. Okay, so here we will mainly consider this approach. Okay, and then another thing that is very important in FSI and in multi-physics problems, how we discretize and what is the representation of the interface on the fluid domain. Okay, so you have basically also two paradigms: fitted meshes, in the sense that basically the interface is, excuse me, just one moment, please. Sorry. So so you have basically fitted meshes in which you have a representation of the interface in the fluid mesh, and so this facilitates, in fact, the discretization of the interface conditions. But as you see here, if you have very large displacement or potential content, you degrade, in fact, the quality of the mesh, and so remeshing is often necessary. Okay. On the other side, you have unfitted approaches in which you have a not at all representation of the interface on the fluid mesh, background fluid mesh, and so you have all the flexibility, but you paid it because now implementing the interface conditions on these frameworks is much more complicated. So in this talk, for the sake of time, I will focus only on this kind of approaches, so partition methods and fitted approaches. Although some of the approaches that we discussed here can also be applied to this unfitted mesh approach. Okay, so and before starting the description of the meshes, I think it's very important to in order to motivate the difficulties of time splitters, to discuss what is the limitations of this approach, which is called Dirichlet-Neumann loose coupling or weak coupling, which basically consists in using your favorite solver in each domain for the fluid and the solid, and then split the interface conditions in the following way. So you see that at time level L, the motion of the fluid domain is basically taken from the previous position of the interface of the solid displacement. Then you can update the fluid domain, and then you solve the fluid with the previous velocity of the solid, and then you can evaluate the fluid stresses and then solve for the solid. So this is the most basic splitting scheme, but which is known to be, in fact, unconditionally stable. In fact, in some physical regimes, you have here an example, in fact, of in the case of a elastic tube. So you have a strongly coupled scheme here and a Dirichlet-Neumann loosely coupled, and you see that after a few iterations is unstable. Okay, so well, this is a very known instability, and basically you can show that in simplified models, this is basically a problem of inertia ratio between the fluid and the solid. If you satisfy this condition, where basically you have the inertia effects on the top and the fluid inertia effect on the bottom with some geometrical information, so this is the eigenvalue of the added mass operator. If you satisfy this, which is, for instance, the case in biofluid flows, because the densities are very similar, the thickness is small and this is very large, is basically the length of the domain, you are always in this case, okay? And the problem is that there are no discretization parameters here, so you cannot tune them to basically cure the problem. And the basic motivation, I mean, the underlying mathematical problem related to this is the fact that when you do loose coupling Dirichlet-Neumann, you basically are treating the added math effect explicitly, and so basically you get that because this term is dominating. Okay, so in order to avoid this, you basically have three options. The first one is to do a strong coupling. So basically you implicitly treat the kinematic and the dynamic coupling, which was not the case there. So if you do that, you have an energy inequality, and so everything is stable and accurate. Okay, but computational demanding because you have two couple problems which are heterogeneous, and there is a vast literature on how to solve that in an efficient way. So either using partitioned method or monolithics. Then another approach is to basically try to limit the cost of the implicit part, and this can be done, for instance, using a fractional step in the fluid, because then you can basically we saw in the previous slide that the problem was the link between the fluid inertia and the solid inertia. And so if you use a fractional step method, you can keep both incompressibility and the solid inertia in the same implicit coupling, and this avoid the previous instabilities. Okay, so these methods are stable and accurate, but of course they require that you use a kind of a specific method in the fluid for the time discretization. And then of course there is loose coupling. Can we do better than before with Dirichlet-Neumann? And the answer is yes. There are several methods that we can stabilize in ficta this split coupling using each method, but it is well known that it's suffering from several accuracy issues, and we can do better. In fact, in the case of thin solids, we can derive this kind of Robin-Neumann schemes that can be proved to be accurate and stable, but as soon as you use thick solid models, you see that you basically retrieve the accuracy issues of this kind of stabilized split coupling schemes. And the main reason is because we lost, in fact, uniformity with respect to the discretization space. So basically the splitting error, refining the mesh, increases the splitting error, okay, which of course we don't want. And then recently there is a solution for that, which is Robin-Robin split coupling schemes that, well, at the beginning was supposed to be suboptimal. So they remove that loss of uniformity, but they are suboptimal in time. And we will show in this slide that in this presentation that we can go to near optimal accuracy. So basically, I will give you an overview of some of these methods. And then I will compare them in some in a specific numerical example. Okay, so we have seen the motivation. So this is the outline of the talk. So basically, I will show you some example of a strongly coupled schemes, semi-implicit methods, and Robin-Neumann schemes. We will compare them in the framework of an experimental setup, and then I will conclude with some ideas on these laws, how we can circumvent this law of uniformity in Robin-Neumann scheme. Sorry. Okay, so a strongly coupled. So basically, an important aspect is the fact that the geometrical compatibility is not responsible of the other mass effect, so we can keep it split. Okay, so this basically is very appealing in terms of computational effort, because we remove all the geometrical nonlinearities in the fluid, so we can move the fluid domain from the previous position of the interface. Okay, and then but then in order to get the stability in the stronger coupled schemes, we basically keep implicitly the kinematic coupling on the velocity on the stresses. So this is, you have to solve this coupled system at each time step. Okay, so it's, as I said before, it's energy stable because you get energy inequality. But the question is how to solve this efficiently, and I said there is a vast literature on partition and monolithic methods for that. So we can reduce the computational cost with semi-implicit methods, as I said before, so projection scheme. So the idea is to use a projection scheme in the fluid. So we do it before. So we basically move the fluid domain from the previous position of the interface. But now we use the fact that we split velocity and pressure in the computation. So the viscous and the convective effects are now, so we extrapolate the velocity. So this is an incremental pressure correction scheme. So we solve for the intermediate velocity un with the previous velocity of the solid, okay, not for the pressure. And now for the pressure system, so the pressure Poisson equation on the increment phi, now we couple it implicitly with the solid. Okay, so you see that now we have an implicit part which is less complex than before, because we only couple the incremental, so the pressure with the solid. Okay, we can show that these kind of methods are conditionally stable. So you can this kind of stability condition, and you see now that you have the parameters tau, discretization parameters tau and h, they come into play. So we can tune them to make the scheme split it. Okay, and again, but you have an implicit part that again can be solved using partition or monolithic methods. This one. Okay, now we move to this Robin-Neumann splitted coupling scheme. So basically here now we allow to have a full split in between the fluid and the solid. And so we do as before, we update the fluid domain from the previous position of the interface. We solve the fluid with this Robin condition here. And I will basically give you some detail, some motivations, where this comes from in the next slide. So you see that everything is known from the previous time step. So velocity in the solid and the stresses in the fluid. And then once we have that, we can apply the stresses on the solid and solve for the solid. So it's fully split in terms of coupling. And in fact, the idea is that this Robin condition here keeps the fluid. You see that the parameter of the Robin condition is what is the inertia of the solid. And this is what guarantees the stability, in fact, for the coupling scheme. And so where this comes from, in fact? Well, the idea is that this only works for the case of a thin solid model. Why? Because in fact, the idea is that, remember that in the case of a thin solid model, the dynamic coupling, so continuous of stresses, appears as a source term. Okay, so, and you see that we have at the same time the continuity of velocity. So we can eliminate the velocity of the solid by putting u here. Okay, so you get that here. So you put that from the left, on the left-hand side, and the LD elastic term on the right-hand side. You see that we have a sort of Robin condition, regionalized Robin condition for the fluid. And now the idea is to say, okay, I want to keep the inertia terms of the solid implicit with the fluid. So you have to discretize this in an implicit fashion. And I want to split fluid and solid. So I treat this part in a splitted fashion. And this is what we get here. Okay, so you see that we treat this part implicitly and the other split it. Okay. And we basically sorry, I don't know what I did here. Yeah, so you see that we get, in fact, unconditional stability, and we can prove that this method is, in fact, first order. This splitting is first order in time accurate, okay? And what is important to note here is that the constant depends on the elastic parameters in the solid. So T is the velocity of the elastic waves in the solid, and the density also here. And you see that epsilon plays a role here. Okay, we cannot, in fact, when we do thick solids, this epsilon becomes the H parameter, so the discretization parameter in the solid, and you see the loss of uniformity that appears here. Okay, and the last scheme now for the comparison is the fully decoupled split scheme, in which basically we combine the Robin-Neumann with a fractional step in the fluid, and we have a full splitting of the state. So we solve, I mean, we update the fluid domain position from the previous position of the interface. We solve for the velocity, viscous velocity in the fluid through the Robin condition, okay? And then we update again the pressure now with a Robin condition in the, you see that everything is known from the previous time step, and now we update the stresses in the solid from the velocity and the pressure, okay? And so this is, we can prove that it's also unconditionally stable in some configurations and allows you to fully decouple the evaluation of the state. Okay, so now in order to compare the different approaches, I'd like to use the basically data from experimental setup. So this was organized some years ago by some colleagues, okay, that you are listed here. And so basically what they did, they put a phantom fluid in a MRI scanner that you see here. So if I zoom, so you have a closed flow here. So you have a reservoir. In fact, they push here fluid on these two pipes, and they have a silicon filament here, and they basically imagine the fluid and the motion of the filament. So everything here is in millimeters. Okay, so and what they provide is the following. So you have the geometry, of course, the inflow profile on the two inflow boundary here, parameter for the fluid, density and viscosity, and for the solid also density and the elongation test. So you have to infer basically the geomodulus and Poisson from this test case. So a few words about the constitutive behavior and material parameters that we have. So for the fluid, nothing new, it's in continuum fluid. So basically the two densities, so it's glycerol, so it's a bit dense than water, okay, and the viscosity here. For the solid is silicon, and well, all this in the previous slide, the solid is supposed to be only elastic, but in fact, I mean, we use a viscoelastic material, so with a Kelvin term of, in fact, on the constitutive law, and you have here the parameters. So it's something Kirchhoff, the simplest, let's say, constitutive law with a Kelvin term here for the viscous part. Density of the silicon, so you see that is lower than in the fluid, so it's going to go up because of the Archimedes principle. And and this is the parameter that you use for the viscosity that we basically tune in order to avoid some unphysical rotational effects on the simulations. So this is the geometry. So we basically prescribe flow. This was measured, in fact, which is a bit surprised because these are basically parabolic profiles that are imposed here that basically we should impose Gomersle, but well, this is what we get from the challenge. And then they provide also pressure on the outlet, so you can basically parameterize this hydrostatic pressure on the outlet through the value of the pressure on a given point. Okay. This is the kind of measures that we use. I mean, with several measures, you have here basically the medium refined meshes. So you have the thickness in the case of a thick solid, and of course, in the case of a shell, you have only the surface. And basically, this is what we use. So Q1 for the solid, or Q1 MIT4, so with this MIT3 treatment of the lock-in, and then P1, SVPG, PSPG for the fluid, with a discontinuous, of course, pressure here that we can create since the mesh are fitted. So we create just a crack in order to keep track of the discontinuity. An important point here is how we move the mesh. Remember that we have to update the position of the fluid domain from the position of the interface of the solid. And this can be done in order to guarantee a kind of robustness in terms of the fluid solver. Okay, so you cannot create incorrect meshes. So what we do here is in incremental, we basically combine some previous approaches with an incremental approach. So basically, we don't update. In fact, what we lift is the increment. Okay, so between two successive time steps instead of the full displacement. And so we basically transformed it on the previous current configuration through the application AM. And then we use a sort of elastic operator. And we basically, you see that the Lamé coefficients are penalized by the volume in order to make rigid, stiffer and stiffer the elements which are very small in order to guarantee that they are not very bad. And then once we have the increment, we update the previous displacement. Okay, so this is the kind of mesh motions that we get. This is, for instance, the initial condition. The solid goes up because of the Archimedes principle. And this is the simulations of this setup. So you have basically a pulsative flow, and then you have the motion of the silicon filament that goes with the fluid. Okay. So a few words on the computational setup. So we basically use a partition approach, as I mentioned to you before. So master-slave implementation. Exchanges are used with PVM or with TheriumMQ we want. And for the fluid, you have PET-C with additive Barth and local ELU preconditioning of the fluid. And for the solid, we use balancing domain decomposition, Neumann, in fact. And so I think here you have basically all the schemes that we have seen. So strongly cooperative with either with the thick solid or the thin solid, semi-implicit, and the loosely coupled, of course, with the shell in both cases, either with mathematic and fractional step. So this is just the name that we number with the other schemes for the next slides. And you see that, well, assume as we introduce splitting, we reduce the computational cost. Some comparisons are of course unfair because we are comparing here semi-implicit and loosely coupled with different monolithic and fractional steps scheme. So we are mixing coupling, splitting in the fluid solid and splitting in the velocity pressure coupling. Okay, so but you see that, okay, as soon as splitting is introduced, we reduce the computational cost. So time is here dimensionless. Okay. Okay, so this is the experimental result that we used for the comparison. You have the motion of the filament here at some time steps, and then you have on some slices of the fluid domain the MRI scans of the velocity. So this is the third component. We see the scale here, so it's the most important. So third is on that direction on the along the tube, and you see the two jets, in fact, that appears okay on the top and the bottom. Okay, so basically you have here in blue the experiment, and in the other colors and with the different figures, in fact, or symbols, the 6 method. In fact, we have remember that for the strongly coupled and implicit and semi-implicit, we have 2 methods because we have both with the shell model and the thin and with the thick solid. Okay, but what basically see here is that basically the results are pretty much the same as soon as the shell or 3D model are fixed. Okay, and now I move and you see that it goes down, goes pretty much. There is a less deviation on the tip, as you see here. Okay, and here is just we plot in time the deviation of the tip. Okay, the last point of the leaflet, and you see a comparison. You see that the experiment. You see that the numerical results are able to basically reproduce the global dynamics, but there is a mismatch. In fact, we lost this part. Well, everything is in millimeters, so it's not very important, but you see that there is a significant delay here. And again, we see that all the schemes, as soon as you fix the solid model, give practically the same results. Okay. Okay, and here we compare the fluid. So we have on the top the experiment, in fact, and and here you have for not for all this, just for the first strongly coupled and the most simplest one, the fully decoupled, the comparison, and you see that we retrieve the jet in all the cases. Okay, you see that there is a light deviation on the Y component. So remember that these are much more small, and so there is much more noise to signal ratio. So it's, but the results are pretty good. Okay. Okay, so now I enter the last part of the talk, in the sense that, well, we have seen that time splitting with lulescopic scheme works pretty well in the case of a thin wall solid, when we couple the fluid with a thin wall solid, but we have difficulties, in fact, when we use thick solids. Okay, and I mentioned this loss of uniformity in the splitting error, and this was the motivation why these kind of schemes were not included in the previous numerical comparison. Okay, so what I want to show you in the next slides, in the remaining of my talk, is how we can avoid this loss of uniformity with robin schemes. And in order to fix the ideas, I'm going to basically just concentrate on a simple model problem. So we basically remove the geometrical nonlinearities, and I remind you that, in fact, this was not a big deal in terms of stability, because we can treat them explicitly without compromising stability and accuracy. So we say that the fluid domain is simple Stokes. It's written the fluid solver is just Stokes, and we're written in a fixed configuration. So we basically are looking to vibrations of the solid, and so we don't have anymore the geometrical compatibility. And for the solid, we have a linear elastodynamics, and so we have a continuity of velocity and continuity of stresses as coupling conditions. And I want to remind you, in fact, the first scheme that basically circumvents this added mass stability uses was the niche-based stabilized splitted schemes that I show you here. So the idea was to use Nietzsche's method in order to understand what was needed to stabilize the splitting, okay, in time splitting. So this is what we do for the solid. So you see here the niche penalty term. So we force continuity of velocity here with the velocity at the previous time step, and you see now the fluid stresses that appears on the right hand side. We treat them splittedly. Okay. So we can solve the solid from that data from the interface on the fluid. So we start with the solid, and then we solve for the fluid that you see here. Again, we retrieve, in fact, the niche penalty term, the stresses. So this is a standard consistency term that is now on the right hand side. We treat it splittedly, and so there is no symmetrization step for the viscous step, but we keep this anti-symmetrization term in the pressure in order to guarantee coercivity. Okay, and you see that we need to add another term, and this is what the niche method is telling you, is that in order to get the stability, you need to control the fluctuations of the pressure in time, and this is what we have here. So you have a weakly consistent term that penalizes the variation in time of the pressure, and this is scaled by h. Okay. Okay, and so this can, in fact, we are perturbing the continuity condition in the fluid. So basically, we are adding some artificially compressibility on the interface. Okay, this is what makes the scheme stable, and so we can prove, in fact, that it is unconditionally stable, as you see here. Energy is bounded by the initial data in the energy norm. Okay, but the problem is that, well, as I told you, this is a loss of uniformity in the splitting error, and basically you have a comparison here of the error. So this is a convergent history. So we the mesh size here in space, and this is the energy error in the solid. And you see that for a strongly coupled scheme, we get first order. And from this stabilized splitted scheme, assuming that you get tau and h of the same order, you stagnate, you don't converge. Okay. Well, and the reason for this is basically you have to look at the splitting error, and you have two terms. One comes from the stabilization of the pressure fluctuations in times, but this is not bad, because basically we have h here, and a Taylor Spencer give you tau here. So basically you get, in this case, you have tau and h of the same order, so you have first order. So this is very good. The problem now here is this one, and this comes from the split treatment of the velocity in the niche penalty term, because if we have we are creating a splitting error of order tau here, which is going to be basically amplified by the 1/h here, and this explains basically what happened. Okay, so one interesting thing, in fact, is that we understood after introducing this scheme that, in fact, we could get rid of this stabilization, in fact, because so this is since we are putting everything on the right-hand side, we don't need this anti-symmetrization in the pressure, and so we basically can remove that term. And well, the problem is that numerical evidence in the 2014 or something like that show us that, in fact, the scheme was stable, in fact, in spite of the fact that we removed the stabilization, but we were not able to prove stability. And in fact, what we have here is that this is, in fact, a Robin-Robin scheme, a pure Robin-Robin scheme, because now we can, at the continuous level, formulate the coupling as is. We basically have the Robin condition in the solid and the Robin condition in the fluid, But, this is very nice, but we see that we still have this problem of uniformity loss because of the 1/h in the splitting, So, well, so the idea, this is an idea that was proposed here, in fact, that, we could, in fact, if this is the problem, what about taking another Robin coefficient, in fact, let's take alpha. And this is what gives, in fact, the Robin-Robin split scheme, where alpha now is a free parameter, but remember that it has dimensions, so it has to be fixed, But, well, now let's choose alpha independently of the discretization parameter, space discretization parameter. So this works, in fact. So you can show, in fact, that this scheme is unconditionally stable, but, well, and it removes, in fact, the loss of uniformity in H. So you have something that now only contains H, in fact, in the only contains tau in the splitting error, But it's suboptimal, 1/2, There are many benefits. I mean, there is another important point, is that this stability is independent of the discretization in the fluid and the solid. So you can use neutrally stable schemes in the solid, and it works in the sense that the scheme is not using dissipation in one of the two domains. The thing is that this the proof, in fact, of stability heavily relies, in fact, on the Robin condition in the fluid, which is, of course, only satisfied point-wise, and so much you have semi-discrete formulations, But we can, in fact, write the scheme in a fully discrete setting in the following way, without compromising stability and accuracy. And the idea is the following. The idea is to use an additional variable, which is here basically the stresses of the solid, of the fluid at the interface, and you update this with the previous Robin condition. So lambda is not anymore the fluid stresses point-wise, it's just a reconstruction of the fluid stresses on the interface. And you can see, in fact, that this is basically a discrete representation of the residual, which is known to be very nice in terms of energy conservation of the interface, So we can put indeed, in fact, that the scheme is stable, and moreover, this is what I mentioned at the beginning, is that, in fact, the scheme is more than suboptimal. It's near optimal in the sense that we can get order tau by paying a constant with a log behavior 1/tau, And the main idea here is to use a specific representation of the solid stresses on the interface at the discrete level, And we need some assumptions. We need to basically construct a contact function in order to lift the test functions, And well, the assumption is this, and of course, we need some assumption on the geometry of the problem, in particular how the interface is. It works pretty well for a flat interface, for instance. And well, what is interesting here now is that these results now suggest some choices for the parameter alpha. You see that if we want to equilibrate the error, you have to take alpha that depends on the Young model, And one example is here, and this satisfying. That was proposed in another work in completely independently with a different scheme. So this is interpreted as an impedance of the on the interface, okay, on the propagation of the waves in the interface. Okay, so some numerical results now. To conclude, so just to show you that we do have this loss of uniformity, we do circumvent the loss of uniformity. So remember, we have here the convergence history. So again, this is the strongly coupled scheme. This was the previous stabilized splitted scheme, and now you see that with the Robin-Robbing, we got something that is, well, sorry, it's difficult to say. It is not really first thought, but it's not bad. But you see that is not as better as the strongly coupled. Okay, and well, you will see another important point is that if you do a second iteration in the coupling, so you solve twice the solid and twice the fluid, you correct, in fact, the Robin-Robbing scheme with one correction. You get, in fact, first order very easily. In fact, as you see here, we retrieve practically the same accuracy than the strongly coupled scheme. So by doubling the cost of the computation, okay. So just a few words about the impact of alpha. We clearly see that there is an alpha, well, and we see it here. You see that we have alpha 1 over alpha. So you see that we cannot take alpha very large and alpha very small because we have a constant that goes up, blows up, sorry. And you see here, okay, we see that basically there is basically an optimal choice between around 500 here, okay. And if we do correction, when correction, you see that we have a larger choice because the scheme, the accuracy of the scheme is greatly improved, okay. Another important point is to understand the impact of the elastic parameters, okay. So this is basically the same curve that before, for different alpha with the large yaw modulus, and look to the fact that we reduce, in fact, if we have a solid which is less stiff, we basically improve the accuracy, okay? And you see that we do retrieve the first order accuracy that we got in the previous result, okay? So we basically, we didn't see it, in fact, the first order accuracy in the previous case because we were not in the asymptotic regime of the delta t because the constant was very high, okay? And if you reduce again, you see that we really retrieve the first order accuracy. And I think I have a few time more for some numerical samples in 3D. So this is the Robin scheme in the previous elastic in the elastic tube in 3D that I showed at the beginning. Remember that Dirichlet-Neumann blows up after a few time steps. Here I compare, in fact, the position of the interface with correction and correction, and you see that there is an important effect, and you see that this is still a mismatch, okay? Because of course we have an important effect of the yaw modulus in the constant in the splitting error. You have another example here. This is a lead-driven cavity with a flexible bottom in the bottom here. And you see the parameters completely different. And in particular, let me emphasize the fact that we have now a lower yaw modulus, so less stiff solid. So we have large displacement, and you see that now we get very close to the strongly coupled scheme. Okay, so so we do see the impact of the elastic parameters in the splitting error. Okay, and this is something that we have also in the case of the Robin-Neumann, because we have, remember, the speed of the elastic waves. So this, of course, depends on the stiffness of the solid. Okay, I think I'm done now. So we have seen several partition procedures for the solution of incompressible free structure interaction, and we compare them and validate them against this FSI setup. And we saw that we have relatively very good agreement between numerics and experiments. And basically, the deal was not basically the numerical scheme, but the model that we choose for the solid, okay? And in particular, we saw that there was a significant deviation with the shell model. And this is rather natural because I didn't mention that at the beginning, but we need to add the Archimedes force on the shell model because a surface doesn't displace any fluid, okay, because we remove the thickness, okay? So we do an approximation here There is another approximation in the fluid, is the fact that we have parabolic profiles in the fluid, and in fact, it should be Womersley. So there are, of course, modeling assumptions that may explain this deviation. An important take-home measure, I think, is we can avoid, in fact, strong coupling without compromising stability and accuracy. There is an important deal in loosely coupled schemes, and I think the matters rather than stability. So stability was an open question for several, for a big period. But now I think the most important tricky problem is accuracy, in particular for high order. Okay. And as you have seen, the deal is there is, I mean, if you choose a fixed solid model, the situation is more difficult, which is natural because you have traveling waves across the thickness. And I think I already emphasized that the fact that the splitting error depends on the size of the elastic parameter. So, and you may need correction iterations if you want to, you have a stiff, very stiff solids, okay. And for Robin, of course, we have the problem of the choice of the Robin parameter. And I think, yeah, the open question now is to go to second accuracy. And I didn't mention that at the beginning, but translating some of these methods in unfitted measures is not trivial at all. And so unfitted measures, in fact, that already introduce a difficulty on the discrete term of the interface condition at the discrete level in space, also complicated splitting in time. And I think I'm done. So I thank you very much for your attention. And I take the opportunity to do a small advertising, is that INRIA is recruiting a lot of people every year since 2020. So 50 permanent positions every year. So if you know junior researcher interested in finding a permanent position in France, I mean, we are looking in my team for new applications. So please pass the message. Thank you very much.
Okay, thank you very much for this talk, Miguel. So there's a question in the Q&A. Can you see that?
Let me look at that. What is the Q&A? One question. Yeah. Wow. Slide 6. Slide 6. Yeah. I assume this numerical instability is due to strong physical interactions. If there are strong interactions between the two different medium also domains, I assume the monolithic approach is favorable, but I have the impression that in many cases for practical, okay. Therefore, I'm wondering if there are studies surveys on the role of the underlying strong physical interactions on the different levels of the solution approach, the top level monolithic approach. Okay, so I think maybe this role between different levels can be exploited to improve the current solution. I mean, I think the underlying question, and you can correct me if I'm wrong. So I think the underlying question is, okay, there is a strong coupling, and so one should use in principle strong. I mean, there is a strong coupling between the fluid and the solid at the physical level, okay, and so one in principle would use a strong coupling at the numerical level, and the answer is yes. But the idea here is to basically understand what we can in fact split and we cannot, okay, in terms of stability and accuracy. So of course, if you use a strongly coupled method, which is here, it is stable because you have an energy inequality. The idea here is